Okay, so we're discussing problem 2 on the term test, which was to find all possible orders of F1, F2 for reflections F1 and F2 in D21. Okay, so first of all, the order of an element of a group divides the number of elements in that group. Yeah, so the order of an element of a group always is the divisor of the number of elements in that group. In this case, so I could say that the order has to be a divisor of the number of elements of D21, which is 42, but you can actually do better. So because you know that the product is a rotation. So since the product of two reflections is a rotation, F1, F2 is contained in the subgroup of D21 consisting of all rotations. And that has 21 elements. There are 21 rotations, right? And they form a subgroup. The product of rotations is a rotation, and the inverse of a rotation is a rotation. Okay, so that means that the order of F1, F2 must divide 21, which is the number of rotations. So the order of F1, F2 can only be 1, 3, 7, or 21. This is apparently where a lot of people were confused. Apparently, I don't know because I didn't grade the question, but a lot of people did get up to the stage of knowing that the product is a rotation and its order must divide the number of rotations because the rotations form a group. They form a subgroup of the dihedral group, which is a group. So the order must divide 21. Or said differently, I mean, if you don't think of subgroups and if you don't want to think about subgroups, the rotations are a cyclic group. So, I mean, it's another way of seeing that it's a subgroup. Is that rotations form a cyclic group with 21 elements. And so the order of any element in a cyclic group divides the total number of elements. And that's true in any group. So the order can only be 1, 3, 7, or 21. And apparently a lot of students did get to this stage. But the mistake that they made was just because the order has to be one of these numbers doesn't mean that these are actually all of the orders, right? It's a bit of confusion in what it means by all possible orders. All possible orders, you're not supposed to include possibilities that don't actually occur, right? Like, or else why can't I say the possible orders are 1, 2, 3, 4, 5, 6, 7, up to infinity? You know, one of those is going to be the order, right? But a lot of those don't work. In the end, you're supposed to tell me exactly which orders do occur. So all that we know is in any group, the order must divide the number of elements. That doesn't mean that every number that divides the number of elements actually occurs as an order. It just means that any order that does occur must divide the number of elements. So it's a subtle difference in the logic. So 1, 3, 7, and 21, we can narrow it down to these values, but that doesn't mean that all of these values occur. In fact, they do, but you have to show that they do. They don't occur by default. So why do they all occur? So we have to show that 1, 3, 7, and 21 all actually occur as an order of some f1, f2. Now, at this stage, it's hard to make any progress unless you remember a fact from lectures, which is that the product, well, we know the product of two reflections is a rotation, but there's a nice form for what rotation it is. So suppose F1 is a reflection through line L1, and F2 is a reflection through line L2, then F1, F2 is a rotation of 2 theta. By default, it always means counterclockwise. Counterclockwise. Where theta is the counterclockwise angle I have to remember this. So L1 makes with L2. So this is L1. This is L2. This is theta. If you reflect in L2, then you reflect in L1. The end result will be a rotation of 2 theta. But it's important that, is it important that you get the angle right? So let's say I took the angle L2 mixed with L1, then I would get pi minus theta. Yeah, so it is important that you pick the right angle. So make sure you look at the angle L1 makes with L2 and not the angle L2 makes with L1. Counterclockwise angle. So make sure you remember the convention. If you draw this picture, it'll be clear. So that's how I remembered it. I don't remember it by default, but I just imagined the situation and I realized, okay, it's since I'm first reflecting through L2, then L1, then it should be the angle L1 makes with L2, like this. Okay, so that's the angle. Okay, now, so we know how a product of two reflections looks as a rotation. What do the rotations look like? And how do we get the orders we want? So I think it's easiest if you remember that the rotations of dn are isomorphic to Zn. This is something you probably already intuitively understood before you even knew what the word isomorphic means. I mean, the idea is the rotations are by angles 2 pi k over n, but really that 2 pi over n, you're always ignoring it, right? Like what you really care about is that k. And all that matters about that k is that when it's divisible by n, it's a trivial rotation, right? You get back to where you started. So really, you were always working in Zn when you were doing rotations. You just now know what the word isomorphic means. I guess you recently learned it, right? So now you know a fancy word for quickly saying what you were thinking. But so hopefully, you don't get confused by me using the word isomorphic. I mean, it's something you already understand, I'm sure of it. If you worked with rotations, it's just a word to quickly communicate it. That fact that you understood, which is that rotations, all you're really doing is mod n arithmetic always, right? Like if you rotate by, so for example, if you rotate by 2 pi, let's say 4 pi over 3, then again rotate by 4 pi over 3, then this is 2 pi times 2 over 3, this is 2 pi times 2 over 3, the total is 2 pi times 2 plus 2 over 3, which is 2 pi times 4 over 3, which is the same thing as 2 pi times 1 over 3, right? Because 2 pi times 3 over 3 is 2 pi, which is just a trivial rotation. So you're always doing mod n arithmetic whenever you're rotating by angles 2 pi k over n. So yeah, so the rotations of dn are isomorphic to Zn. So we can work with Zn. I mean, I could work with just these angles directly, but like it just makes my life harder because in the end, I really am just working with Zn. So why not just directly work with Zn and not keep saying 2 pi over n? Because we really just care about the k, right? That's all that actually matters when we're doing these calculations. Like who cares if pi is 3.14159 or whatever? Really what matters is that k and the n. Those would actually matter when you're discussing rotations. The precise angle is not important because we're working with discrete multiples of 2 pi over n. Okay, so so in this case, we're working with Z21. Okay, so how do you get an element of order 3 in Z21? So let's see. Elements of order 3 in Z21. There's 7. There's 14. And that's it. So to get so for F1, F2, and okay, let me translate these to rotations now, to angles. So these are rotating 2 pi times 7 over 21 and 2 pi times 14 over 21. Okay. So for F1, F2 to have these, so for F1, F2 to have order 3, let's pick one of these. Let's pick whichever one looks simpler. I'll just pick this one. So we'll pick this element. Well, this will be our target because we're trying to get a rotation that has order 3. So for F1, F2 to have order 3, we need 2 theta. Theta is the angle between them. 2 theta to be 2 pi times 7 over 21. So I can rewrite this as 2 pi times 14 over 21. And then I'll get theta equals 2 pi times 7 over 21. See, even in this step, I regret even talking about angles because this is much clearer in Z21, right? Because why didn't I just divide 2 pi times 7 over 21 by 2? Then I would get 2 pi times 7 over 42. But that's not actually a possible angle that 2 lines can have in the dihedral group, right? Like if you look at the lines you can reflect, all the possible lines, that angle is not a possible angle you can get. So really, maybe it is best to just stick in Z21. So maybe I'll do that. No, I'll just keep going. I'll just keep translating between the two contexts, even though that makes it a bit more confusing in my opinion. But I would have to tell you what, because right now it's the translation between rotations and elements of Z21 is clear. It's a bit, it'll take a bit of time to explain why reflections, how do I translate between that and Z21. But the point is, I guess, practically, when you divide by 2, make sure the angle you get is actually a possible angle. So I guess if you want to be systematic, I won't pick any of these, and I'll just try both. And one of them will work ideally. So we can have 2 theta equals 2 pi 7 over 21. So then theta equals 2 pi times 7 over 42, which is not what I want. So this is invalid. And why is it invalid? Because I can draw it. I can't draw D21 because it's too big, but I'll draw, let's say, D7. Oh, you did? Oh, yeah. Well, at least, you know, you weren't the only one. A lot of people got marks off for this question. So if you have 2 reflections in, let's say, D7, the angle must be a multiple of 2 pi over 7. So that's the case here as well. In D21, the angle has to be a multiple of 2 pi over 21. So you can't, this solution is invalid. Of course, the solution, if you're thinking mod 21, it all makes sense, but let's just stick with angles because it would take too much time to get into that. But maybe I'll do that in my other section and you can look at that. I don't know yet, but right. So you just have to cross out invalid angles. So this one doesn't work, but there's another option we could try, which is 2 pi times 14 over 21. So let's try that. So 2 theta equals 2 pi times 14 over 21. Then theta equals 2 pi over 21. And that's valid because it's a multiple. So this was not valid. So, and then how do I get 2 lines that make this angle? They're just 2 lines that pass through adjacent vertices, right? So if you look at like Z21, D21, say this is 1, this is 20, this is 2, this is 21, and let's say it just keeps going, I can't finish the picture, then you just take, so you want the angle that L1 makes with L2 to be 2 pi over 21, right? So we can take this to be L1, this to be L2, and this angle is 2 pi over 21. So make sure, I guess there are a couple of ways you can go wrong for this question. One is using an invalid angle. And like, for example, for order 3, if you only try 2 pi 7 over 21, maybe you would have thought that there's no element of order 3. So that's one way you could go wrong. And then there's the little thing, which is you have to remember which line is making an angle with which line. So since we're reflecting through L2, then L1, it's the angle that L1 makes with L2. That's the angle that matters because you're reflecting, you know, like look at this blue vertex, it's reflecting to L2, then L1. So the total rotation is 2 times the angle that L1 makes with L2. Okay, so that's how you get an order 3 element. How about now, what about order 7? So we list the order 7 elements of Z21, those are 3, 6, 9, 12, 15, 18. So the angles, and these correspond to angles. So angles are 2 pi times 3 over 21, 2 pi times 6 over 21, 2 pi times 9 over 21, 2 pi times 12 over 21, 2 pi times 15 over 21, and 2 pi times 18 over 21. Ideally, you can immediately see which one I should try that will give me a valid angle. But worst case, you're not going to have to try that many things until you get a valid angle. So let's try 2 theta equals 2 pi times 3 over 21. Get theta equals 2 pi times 3 over 42. That's not valid. But the next one we try is going to work. So as long as it's an even number, it'll work, right? So 2 pi times 6 over 21, you get theta equals 2 pi times 3 over 21. So that's valid. And then how do I actually get that angle? It's easy. So I need one line to be 3 steps away from the other line. So 1, 2, 3, 4, 21, and then imagine all the other vertices were drawn. So L1 should make an angle of 2 pi 3 over 21 with L2. So this should be L1, and then this should be L2. And then this angle is 2 pi times 3 over 21. So then in this case, F1, F2 is the rotation by 2 pi times 6 over 21, which has order 7. How do I get order 21? So the order 21 elements of Z21, they're all the elements that are relatively prime to 21. They have no common factors with 21. So that's 1, 2, 4, 5, 6, 8. Oh, not 6. 8, 10, 11, 13, 4, no, not 14, 16, 17, 19, and 20. And the angles, you hopefully, they're just 2 pi over 21 times all those. And then you can tell now that the even ones will give you a valid angle. So let's say 2 theta equals 2 pi times 2 over 21, then theta equals theta equals 2 pi over 21. Didn't we already get theta equals 2 pi over 21? I must have made a mistake. What did I do? Oh yeah, I made a huge mistake. So I wrote 2 theta equals 2 pi times 14 over 21. And then I wrote theta is 2 pi over 21. Okay, so that's a huge mistake. I'll fix that. So it should be 7. And this picture is wrong too. Yeah, so if you feel bad about messing up that question, I mean, I messed it up right now. So I'm no better. So it should really be 7 steps ahead. So this should be This picture is a bit of a lie, but whatever. I mean, it's inaccurate. It's not drawn to scale, but this was what they would look like. So this should be L1 and this should be L2, and the angle should be 2 pi times 7/21. By the way, if you want to communicate about the dihedral group, the picture is not the right way to do it. Just have a good notation for the reflections. So just say, let SI be the reflection through the line passing through vertex I. And then you can just easily write, let F1 be S8 and let F2 be S1. So that's much easier than drawing these pictures, but I just drew them to be, as I guess, because it wasn't that bad. But in some situations, the dihedral group might have a lot of elements and you won't be able to. Okay, and then, okay, now it's really 2 pi over 21. So 1, 2, and this will be L1, this will be L2. The angle between them is 2 pi over 21. Okay, and then there's the order 1 element. That's easy. So order 1, that's just the identity. So the angle is 0. You solve 2 theta equals 0. You get theta equals 0. So you get L1 equals L2. So if you just repeat a reflection, you get an element of order 0. I mean, order 21. I mean, order 1. So if F1 equals F2, then F1 times F2 is just the identity, which is the rotation, which has order 1. So all orders 1, 3, 7, and 21 are actually possible. I think in my next section, I'll do this all in terms of modular arithmetic, and maybe that'll make things clearer. So if you want to see a solution that only, like, I won't even talk about angles in it. So if you want to see a solution like that, please check out the notes for the other sections, and hopefully maybe that'll be clear to you. It's just I guess, because the dihedral group is something discrete, you know, some number of steps. These angles, you don't really need to think about 2 pi and all these things. So you can just make everything discrete. I don't know if it's that helpful, but I prefer it. Okay, are there any questions? Okay, so next, conjugation. Conjugating permutations is super easy. So it all comes down to a simple fact. If pi is a permutation, okay, if sigma and tau are permutations, then sigma tau sigma inverse sends sigma of I to sigma of tau of I. And the proof of this fact, and I is from 1 to n. The proof of this fact is really easy. Just apply sigma tau sigma inverse to sigma of I. So sigma tau sigma inverse of sigma of I is sigma tau sigma inverse sigma of I, and these cancel out. So it's just sigma of tau of I. And what this means is whatever sigma, whatever tau does, sigma tau sigma inverse does, but just shifted by sigma. So like if tau sends I to j, then sigma tau sigma inverse sends sigma of I to sigma of j. In particular, it's really easy to find the cycle structure, the cycle decomposition of sigma tau sigma inverse. So in particular, to find, and by the way, the reason why I wrote this fact and this proof is just because it's tough to remember things, right? Like, is it sigma tau sigma inverse or sigma inverse tau sigma? Especially like for me, I haven't taken group theory in years. So how do I remember it? Well, I can't remember all these facts literally, but if I remember the justification for it, then I can rederive the fact. So I remember that the justification had to do with sending sigma of I to sigma of tau I. And then I know that it's sigma tau sigma inverse, because that'll get this cancellation here. So if you have sigma tau sigma inverse, then you do sigma of I, the sigma inverse and sigma will cancel to get sigma tau of I. But if it was the other way around, so sigma inverse tau of sigma, you wouldn't get the cancellation. So these facts do have these facts and proofs do have value in terms of memorizing things. But yeah, in particular, is to calculate the cycle decomposition of sigma tau sigma inverse, just apply sigma to, well, I should put it in quotations because it's not clear exactly what I mean, but it's clear from the example. So you just apply sigma to the cycle decomposition of tau. So for example, let's say tau is 1 to 1735, 268, 9. What element do I have left? 4. And let's say sigma is 1, 2, 3, 4, 5, 6, 7, 8, 9. What did it send it to? Let's say it sends 1 to 4, 1, 8, 6, 9, 3, 7, 2, 5. Let's say that's sigma. So then how do I get the cycle decomposition of sigma tau sigma inverse? So you start with the one for tau. It's 1735, 268, 94. And that's the point of what I wrote before. So tau sends 1 to 7, it sends 7 to 3, it sends 3 to 5, and so on. Sigma tau sigma inverse will do the same, but with a sigma in front of everything I just said. So we'll say it'll send sigma of 1 to sigma of 7. It'll send sigma of 7 to sigma of 3. And what is sigma of 7? What is sigma of 1? What is sigma of 3? So you just apply sigma to each of those elements. So sigma of 1 is 4. So I'll draw these arrows to show I'm applying sigma to each element. So 1 goes to 4 under sigma, 7 goes to 7, 3 goes to 8, 5 goes to 9, 2 goes to 1, 6 goes to 3, 8 goes to 2, 9 goes to 5, and 4 goes to 6. So that's sigma tau sigma inverse. And it goes back to the fact I said. So the whole point of sigma tau sigma inverse is it's like sigma, but it sends, if sigma sends, it's like tau, but if tau sends I to j, then sigma tau sigma inverse sends sigma of I to sigma of j. So tau sends 1 to 7, 7 to 3, 3 to 5, 5 to 1. Sigma tau sigma inverse is the same, but with a sigma in front of all that. So it sends sigma 1 to 7, sigma of 7. So it sends 4 to 7. It sends sigma of 3 to sigma of 5. So it sends 8 to 9. It's verbally a bit awkward to say, but hopefully like it's clear what you do, right? You just apply sigma to every element in the cycle and you get the new cycle decomposition. And this works in reverse too. So like, what if I asked you, given tau 1 equals, let's say, 2, 7, 8, 10, 1, 3, 6, 9, 4, 5, and tau 2 equals, I don't know, I just have to pick some random numbers. 1, 5, 3, 8, 9, 10, 4, and 2, 6, 7. Let's say I ask you to find a sigma such that tau 2 equals sigma tau 1 sigma inverse. It's easy. It's just the reverse. You just reverse what we did. So we know that sigma tau 1 sigma inverse will just be tau 1, but you replace every element in each cycle with its image under sigma. So to get tau 2, we know what sigma must be. Well, actually, sigma can have many choices, but we know one easy choice, which is just based on how they're written. So I'll just make sigma send 2 to 1, 7 to 5, 8 to 3, 10 to 8, 1 to 9, 3 to 10, 6 to 4, 9 to 2, 4 to 6, and 5 to 7. It's the obvious choice. So now if I apply sigma to tau 1, if each element in each cycle I replace it with its image under sigma, I'll get tau 2. Like I chose the sigma exactly so that happens. I know this choice is not unique. There's multiple sigmas that work. So because there's multiple ways to write each cycle, so you could rewrite, for example, you could rewrite tau 2 as 5, 3, 8, 1, 9, 10, 4, 2, 6, 7. Now that gives you a new choice of sigma. So now you could take sigma to be 2 goes to 5, 7 goes to 3, 8 goes to 8, and 10 goes to 1, and the rest is the same. So there's a bunch of choices for sigma, but the point is that permutations that have the same cycle lengths are conjugates of each other. And how you conjugate them is by just mapping the elements of one cycle to the elements of the other cycle. Okay, and there was a question we were supposed to do, which is from your practice problems for the term test, which is to find, so practice, we have to find sigma tau to the negative 500 sigma inverse. So sigma is 16572 and tau is 3672 1081 549. 1081 549. Okay. So first I have to find tau to the negative 500. And to do this, we use the cycle decomposition of tau. So tau equals 1 goes to 3, 3 goes to 7, 7 goes back to 1, 2 goes to 6, which goes to 8, which goes to 5, which goes to 10, which goes to 9, which goes to 4, Wow, it's a long cycle, and it goes back to 2. Okay, so we can depict tau as, you can draw like arrows and dots to kind of imagine tau. So for tau, it sends 1 to 3, 3 to 7, and 7 to 1. And it also sends disjointly 2 to, what was it? 6, 8, 5, 10, 9, 4. So 6 to 8 to 5 to 10 to 9 to 4. Did I copy that down right? Yeah, 2, 6, 8, 5, 10, 9, 4. Okay, so that's tau. First of all, getting tau inverse is super easy. For tau inverse, just reverse the arrows. So for tau inverse, it's the same thing, but with the arrows reversed. So 1 will now go to 7. 7 will go to 3, and 3 will go to 1. And the same thing for this other one. Now, so for each application of tau inverse, we're moving 1 step along the arrows in each of these cycles. So tau to the negative 500 is 500 applications of tau inverse, which means move 500 times along the arrows in each cycle. So in the first cycle, it has length 3. So we'll write 500 is 3 times 166 plus 2. So if you move 500 steps, you'll just go back to yourself 166 times, because every 3 steps you get back to yourself. And then you move 2 additional steps. So 1 will go back to itself 166 times. And then I'll move 2 steps. So it'll go to 3. So 1 will go to 3. Similarly, 7 will move 2 steps. So it'll go to 1. And 3 will go 2 steps. So it'll go to 7. And the other cycle has length 7. So we write 500 is 7 times 71 plus 3. So every element, for example, 2, will go around the cycle 71 times. It'll keep just going back to itself 71 times as you apply 500 applications of tau inverse. And then for the last 3, you'll just move 3 steps along the arrow. So it'll go to 10. So 2 will go to 10. Same with 4. So 4 will go around the circle 71 times for the first 497 applications. And for the last 3, it'll just go to 9, then to 10, then to 5. So 4 goes to 5. And hopefully you get the point. So 9 goes to 8. 10 goes to 6. 5 goes to 2. 8 goes to 4. And 6 goes to 9. So 3 arrows away. So now we know what tau inverse is. So tau to the negative 500. So tau to the negative 500 is 1 goes to 3, which goes to 7, which goes back to 1. And then 2 goes to 10, which goes to 6, which goes to 9, which goes to 8, which goes to 4, which goes to 5, which goes back to 2. So that's what tau to the negative 500 is. Two, 10, 6, 8, 9, 2, 10, 6, 9, 8, 4, 5. And then we just have to remember what was sigma. So sigma was some 16572. And then I told you the rule for finding sigma tau to negative 500, sigma inverse. You just apply sigma to every cycle. So let me show that happening. So sigma tau, sigma inverse, sorry, sigma tau to negative 500, sigma inverse. So first I write tau to negative 500 on top. It's 1, 3, 7, 2, 10, 6, 9, 8, 4, 5. And then I apply sigma to everything. So, okay, where does 1 go under sigma? It goes to 6. 3 is not touched by sigma, it goes to itself. 7 goes to 2. 2 goes to 1. 10 is not moved by sigma. 6 goes to 5. 9 is not moved. 8 is not moved. 4 is not moved. And 5 goes to 7. So that's the final answer. Okay, so that's all we can get through today. Are there any questions? Okay, thanks for coming, guys, and have a good week. Bye. Stop recording.